and indeterminism.
Good morning, everyone. Thank you for giving me this opportunity to give this talk and this very nice conference. And thank you, Vilasini and Nielsen, for these fantastic talks before me. I'm going to talk about superluminal transformations and indeterminism. And my talk is color-coded, so like the slides about superluminal transformations will appear in blue, the slides about indeterminism is going to appear in pink, and the slides about our no-go theorem, or the result of that we are going to talk about, is going to appear in this yellowish, orangish color. So, superluminal Lorentz transformation. So now, if you have this special theory of relativity, it gives two postulates. One is that the speed of light is the same in all reference frame, and the second is the principle of relativity. Now, if you have linear transformations where the inverse is given by sine flip, then you will have these relations between the coefficients. One will be the symmetric one, which gives rise to the subluminal Lorentz transformation, which we usually call the Lorentz transformation. And the another will be the superluminal Lorentz transformation. Now, the superluminal Lorentz transformation has a very interesting fact that the space and time at infinite limit switches. Now, why is this interesting? So, a few years back, a very famous paper came out known as this quantum principle of relativity by Dragan and Ekert. Their argument can be seen something like this picture. So let's say at point A, some observer has a very local and deterministic description of emitting a tachyon or a superluminal particle, which goes to B. But since it is a superluminal particle and you do not want to have superluminal signaling, at point B there is no local deterministic explanation of when it is coming. Now, this situation under a subluminal reference frame transformation can look like B is the sender and A is the absorber. But then B will be spontaneously sending this tachyon or the superluminal particle. Now, to not have any preferred frame of reference, what they suggested is that you give up local determinism everywhere. But they also go one step further. They not just claim that local determinism is absent, but they also say that the local determinism that you give up is the same local determinism you give up in quantum theory. And they also postulate that you would be able to get quantum probabilities from it. So this got us interested. Now, there are some fundamental limits on getting information about some events. And such is represented by this theory of acyclic causal graphs, GT, which is dependent on the events, then this set of potential causal edges, of which a subset are the events, and propensities, which are the weights of a particular event for occurring. Now, for this particular configuration of events and nodes and the connections between them, if you want to have an informational measure in terms of Kolmogorov quantities, then you can write that the information in the past is the information you get from the events, plus the propensities dependent on the events, up to a coefficient, Cp and Cf. Based on this structure of this acyclic causal graph under superluminal transformation, we came up with a no-go theorem. I'll go one by one now. So the first point of the no-go theorem, or the 0th point of the no-go theorem, existence of non-order preserving SpTs. Now, SpTs are superluminal transformation. A subset of superluminal transformations are superluminal Lorentz transformations, which are linear. Now, if you look at these two event points, 1 and 2, under any subluminal Lorentz transformation where you can come as close as you can to the light, you will still have the ordering preserved. So 1 will always occur before 2. But under superluminal Lorentz transformation, you can also have the coordinates swapped, like I told in the beginning. But then the ordering is also can change under a superluminal transformation, and 2 can happen before 1. An example of that is, of course, the SPLT, or the superluminal Lorentz transformation. So this is what is a non-order preserving superluminal transformation. Now, principle of finite information. So in the world there should be a finite amount of information in a finite amount of volume. And so the total amount of information that is present in the world should be limited by n bits. Then time symmetry of total information. So since all the dynamic laws that we know of now, including Schrodinger equation, Newton's laws even, all of them are time symmetric. So just from the laws, you would expect that the amount of information that is stored in the past from my present point to the amount of information present in the future should be almost equal. Now the past holds memories. So the recently occurred events in the past, you already know if they if they have happened or if they have not happened. So they have propensities either 0 or 1. So they can be compressed more rather than the future events which have propensities in rational numbers between 0 and 1. Hence, the propensities of the past with respect to the events is less than the propensities in the future with respect to the events. And then time has a special role in every reference frame. So every reference frame might not agree about the decomposition of space and time, especially in the presence of superluminal transformations. But what they have to do is that once I'm in a natural reference frame, I will have a specific decomposition of my space and time. And now whatever I call the time coordinate, I should define my light cone in such a way that all time-like points should be within that light cone. So if we have all these assumptions, then we see, and let's say that we agree that all these assumptions can agree. Then we just need one example to prove that all of them doesn't agree. And this one example is the certain embedding of these events. So under this embedding of this certain events from E1 to E7, if we have that the total amount of information is finite and is limited by n, the information is equally spread in past and future, and the past has memories, and there is a meaning of time, then you would expect that the past should have more number of events than the future. But when you do a superluminal transformation, and you have all of this, then you will get that the past and then you can arrive at a situation where the past and the future has the same number of same amount of information from the events, which gives that either we have to violate the fact that the total amount of information is limited, or the fact that the amount of information in the past and the future are more or less the same. Now, there will be certain relaxation of assumption which can give us different interpretation. And I will only discuss one of them for the interest of time, which is the violation of principle of finite information. Now let's look at an alternate situation. Let's talk about orthodox classical information, or orthodox classical determinism. So in an orthodox classical determinism, or the general classical theory we talk about, we have an initial condition given by n tuple of real numbers, and then the dynamic laws given by ordinary differential equation, which uniquely tells you what is the past and the future. But this obviously involves principle of infinite precision, because the initial conditions are given in real numbers, and the mathematical language you speak gives volume about the physical interpretation you're given to give about a particular theory. Real numbers are rational numbers and irrational numbers. Rational numbers, you can do a bijection to natural numbers and they're countable. But irrational numbers, only there are finite algorithms with which you can get the values of pi, root 2, blah, blah. But there are so many other irrational numbers which mathematically should be having infinite information, but physically is bounded by the finite information postulate. So if you don't have infinite precision and you have finite principle of finiteness of information density, you get this kind of alternate classical physics, which Flavio De Santo and Nicola Gisson came up in a series of papers, where you see that classical theory also gives up some sort of an ontic indeterminism. Now, why this is interesting? So we have classical determinacy with real numbers, which has infinite information. Now, something about superluminal transformation, which we did in one of our previous papers, is that superluminal observers or superluminal, under superluminal Lorentz transformations, you can go from a positive energy point to a negative energy point. So the positive energy and negative energy are Lorentz transformable, which doesn't make sense and gives rise to the negative energy problem. The solution of that is to expand the space of the total energy and map all the negative energy to a positive energy dome. So in this expanded space, you will still have to compare the real number values of the velocity with this quantity and map this accordingly, for which you will again need infinite precision for superluminal transformation. So the moral of the story is that if you want to avoid the negative energy paradox of superluminal transformation, you will need again infinite precision, and hence do we have a deterministic theory like orthodox theory, or do we have finiteness of information and of indeterminism? So again, what we came up with the theory of SpTs, is it deterministic or is it indeterministic? Okay, it is indeterministic if you believe that the principle of finiteness of information. But is this indeterminism the same as quantum theory, which is the question we wanted to answer, because this famous paper that I was talking about in the beginning of my talk. But the answer is no, because in quantum theory you have indeterminism because of incompatible measurements and measurement postulates, yada yada. But here the limitations, or the reason you're getting indeterminism, is only because of the limitation of the total amount of information. And these are some past and future direction. Sorry for this disturbance. So this is one of the paper on superluminal quantum reference frame, which we have now published. And this is the talk I was giving about. And then we are also having a paper with Matthias and Vilasini, which we are going to do. And thank you.
Any questions? Yeah. Katrine.
Thank you.
Hi.
Is this working? Thanks very much for this very nice talk. I have a question about one of the assumptions of your no-go result. I think it was number 2, about the time symmetry.
Mm-hmm.
If I believe in some form of block universe picture, is there any good reason? I mean, doesn't this mean that I'm somewhere in the middle of the block universe and there's as much that happened and as much information stored about past events than there is about possible future events? Like, can you make a better point for why I should be exactly in this point in the middle? Or if maybe I misunderstand what this assumption means.
No, like if you, so like the laws, like force equals to mass into acceleration, it involves time, right? So with this, like just because you can expect that you will get same amount of information if you go forward 10 seconds after, than if you were coming from the other direction and you go in the 10-second backward. Like, it's not like a block universe, it's more like a growing block universe. You see, like I think that like the ones yesterday Professor Faydocker was talking about, so it's along that
Right, but just
motion.
because the laws are symmetric doesn't mean that like there's still an error of time, and there's things that have happened and there's things that will happen.
But this is not the accessible information, this is the expected information. The accessible information can be different, which is why the past has some memory saved. So what is actually happening can be different, but like but the total amount that you would expect should be approximately same.
We can discuss more later. Thanks.
Maybe one more question? Or if not, let's go on to the next speaker, please.